Hello everyone. Today I want to give you very brief review for the quiz number 5. Okay, and this review help you to prepare for your final exam also. Okay, so whatever I told you in my lecture chapter 33, 34. Okay, you have a final exam next week. Okay, so there is no third exam because that video was from my last year lectures. So you have, everybody, you have an exam on Friday next week. I think that is July 23rd, and you have a quiz number 5 on Wednesday, that is July 21st. So please don't miss the quiz next week, don't miss the exam next week. Very important. If you miss the exam, you fail the class. That is very important. And I cannot give you the makeup because next week is the last week of this semester. Friday is the very last day of the semester. So I cannot give you the makeup. Anyhow, you have to complete the quiz and the test next week by Friday. Okay. So now your quiz number 4 is basically from, sorry, quiz number 5, not 4. Quiz number 5 is basically from photoelectric effect. Okay, and the nucleus, atomic model, nuclear reaction, special theory of relativity. So simply if you read this photoelectric effect, you know the photoelectric effect, the ejection of electrons when you shine the metal surface. Okay, if the light strike on the metal surface, then the electrons are ejected from the metal surface. That is called as the photoelectric effect. But you know, the incident photon, that must have a certain minimum energy to knock out the electrons from the metal surface. So the equation is, you can write down like, I don't want to draw the diagram here, simply the energy E, this is the energy of the incident photon, like let us suppose if this is your metal surface and if this is the incident photon and electrons are ejected from here, this is your photoelectron. So this is the energy of the incident photon. E, this is equal to Ke max. This is the maximum kinetic energy of the photoelectrons plus omega 0. Okay, so this incident photon has an energy hf. H is the Planck's constant and kinetic energy Ke max plus omega 0. This is the formula. Everyone, you need this formula. Okay, so H here, this is a Planck's constant. This is 6.626 times 10 to the power negative 34 joules second, and is called as the Planck's constant. You need this number. I don't give you in the exam. Okay, this is Planck's constant. F, this is your frequency. Ke max, that is your kinetic energy of the photoelectron, maximum kinetic energy. If necessary, you can write down Ke max. This is equal to 1/2 mv max square. This is mass of the photoelectron. The photoelectron is same as the electron, and you know the mass of the electron is 9.11 times 10 to the power negative 31 kg. And omega 0, this is a work function. Okay, work function, and this is equal to F0. F0 is the threshold frequency. If you have to calculate the threshold frequency, you need this formula. Work function is equal to Hf0. Work function. What is work function? The minimum energy required to knock out the electron from the metal surface. That is called as the work function. It is the characteristics property of the metal. Different metal, they do have a different work function. Okay, so minimum energy you need to eject the electron from the metal surface, that is called as the work function. Simply I write down omega 0, which is equal to H times F0. Here F0 is the threshold frequency. This is your threshold frequency. Okay, so the minimum frequency required to eject the electron, that is also called as the threshold frequency. Okay, so here you see the energy HF. Okay, simply in photoelectric effect, the work function, the energy, people they measure in electron volt. Electron volt, you know the unit of energy, like a 1 electron volt. This means this is equal to 1.6 times 10 to the power negative 19 joule. Okay, if you have to convert electron volt into joule or joule into electron volt, you need that relationship, electron volt. And here you have, look at this, HF, the energy of the incident photon E, this is equal to HF. But you know that F equal to C divided by lambda. Okay, what is C? C is 3 times 10 to the power 8 meter per second. And lambda is the wavelength of incident photon. Okay, lambda is the wavelength of incident photon. So if you want to calculate this HF, this is AC divided by lambda. Okay, so here this, you know, H is 6.626 times 10 to the power negative 34 joule second. C is the speed of light, which is 3 times 10 to the power 8 meter per second, and lambda is the wavelength, and wavelength is simply given in like a wavelength, for example, let us suppose 350 nanometer. Any number, okay, any number, not necessary to be 350 nanometer. Any number, 650 nanometers, like a different light, they have a different wavelength. And if it is given 350 nanometer, you have to convert this into meter as needed only. Okay, 350 times you have to multiply by 10 to the power negative 9, because 1 nanometer is 10 to the power negative 9 meter. Then please note this, 1 nm, this means nanometer. 1 nanometer is equal to 1 times 10 to the power negative 9 meter. Then okay, so this number for you, you can do something like this. HC, if you plug H and if you plug C and if you convert that into electron volt, you get 1240 electron volt times nanometer. Divide this by lambda, whatever lambda given. Okay, lambda is, if it is given in nanometer, for example, if lambda is, let us suppose HF, this is HC divided by lambda. I said this is 1240 electron volt nanometer. And if your lambda is 350 nanometer, this is not constant, okay, different light, they have a different number. Okay, so if that is 350 nanometer, then in this case, look how easily you can do it. You don't have to convert this nanometer, because this nanometer and this nanometer you can cancel out, and your result is 1240 divided by 350 electron volt. That's it. You can use your calculator. So then your result, your energy is, you get in electron volt. So if you need in electron volt, you can plug this number also, or simply plug H, plug C, plug lambda. If you plug this H is 6.626 times 10 to the power negative 34 joule second. The speed of light is this much, 3 times 10 to the power 8 meter per second. Then if you plug lambda equal to 350 times 10 to the power negative 9 meter, In that case, your HF you will get in joule, but that joule you have to divide by 1.6 times 10 to the power negative 19, and that is converted into electron volt. Don't confuse, you need to know this very carefully, okay? So this is about the photoelectric effect. You can watch the lecture also available in Canvas page, okay? And let us talk about the atomic model first. There is like a early atomic model, okay? Early atomic model is simply the atom is like the cloud of positive charge. This is the cloud of positive charge, not negative charge, positive charge. So here you have like this is a positive charge. So this is a positive charge, cloud of positive charge, spherical cloud of positive charge, and the negative charge is distributed like this. Something like this, like a plums in a pudding. So this is also called as the plum pudding model. That's it. This is the very early model of the atom. Okay, so this is really simple one, and there is another one, Rutherford model, a Rutherford atomic model. Okay, this is little bit important. What is the Rutherford atomic model is? Rutherford, he first did one experiment. Here is this is a very thin gold foil. This is gold foil, very thin gold foil, and right from here, he took the alpha particle, the beam of alpha particle. This is alpha particle. What is alpha particle? Alpha particle is helium nucleus. You write down like this. Helium nucleus. Alpha particle is the helium nucleus. It has a positive charge. Then what happened? He sent the beam of alpha particle here, like this. But what did he find is most of the alpha particles they pass like this through the foil. Most of the alpha particles they pass through the foil without any deflection, no deviation. They simply pass through the this gold foil. Some of them they return. Some of them, very few only, they return. So what did Rutherford, conclude is because many alpha particles they pass through the thin gold foil, and he concluded that most of the atom, the most part of the atom is empty. The most part of the atom is empty. What does that mean? That means, look at this. There is a nucleus. This is, here you have a proton and neutron, and there is a electron here. So look at this. This area is empty. That is what he meant. So most of the alpha particles they pass through the gold foil without any deflection. Simply they pass through. That means the atom, the most part of the atom is empty. Because here there is nothing here. There is nothing here to deflect the alpha particle, which is positively charged. That is why he said the most of the atom, most part of the atom, most portion of the atom is empty. And very few, they reflect. Why? Look at this. If the alpha particle go there, if this is alpha particle is positively charged, and this nucleus is also positively charged, then what happened? Reflect. Okay, or if another alpha particle right from there, so it can go something like this. So from this experiment, he concludes that the second point is very few alpha particles they reflect. They reflect, or you can say they deflect, they deviate from their path. The reason is very small portion of the atom in the central part, there is a positively charged region. The very small portion, that positively charged region is nucleus. That is what Rutherford he discovered. Okay, so this is about the Rutherford model, atomic model. And there is another one. Another one is the really important one, and the scientists they also accept this model. We call the Bohr's model. There are postulates of Bohr model, atomic model. Okay, what are they? What are the postulates of the Bohr's atomic model? The first one is the electrons, they are moving in a circular path. You know that the electrons, they are moving in a circular path about the nucleus. Okay, but all orbits, they are not possible. You have only certain permissible, allowed orbits. Only certain orbits are allowed. Okay, the first postulate is electrons are travel in a electrons travels in a circular orbit about positively charged nucleus. However, only certain orbits are allowed. The electron doesn't radiate energy when it is one of the orbits. Okay, the Bohr's first postulate. I'm talking about the postulates of the Bohr atomic model. The first postulate is the electron travels in a circular path, okay, about positively charged nucleus. The nucleus is in the center. Okay. However, all orbits are not possible. All orbits are not possible. Only certain orbits are possible. So we call that permissible orbit or allowed orbits. And when the electrons are moving in a circular path, we call those orbits are stationary orbits also. And electron doesn't radiate any energy. When electron is moving in a circular path, it does not radiate any energy. No energy release. That is the first postulate. Okay, that is the first postulate. And the second postulate is only those orbits are possible where the angular momentum of electron is. The second postulate, only those orbits are possible where the angular momentum of electron, this is L, angular momentum of electron is mvr. We did this in mechanics, angular momentum. The angular momentum is integral multiple of h over 2 pi. N is the number, integral multiple, like you can say n equal to 1, 2, 3, 4, and so on. So the only those orbits are possible for which the angular momentum is integral multiple of h over 2 pi. The angular momentum is integral multiple of h over 2 pi. Only those orbits are possible. If your angular momentum L equal to n times h over 2 pi, then that orbit is possible. Otherwise, it is not possible. What is n? N is 1, 2, 3, 4, etc. We also call it as the principal quantum number. Okay, n 1, 2, 3, 4. We call this is a principal quantum numbers. You don't need to know that. There are 4 quantum numbers: principal quantum number, orbital quantum number, magnetic quantum number, and spin quantum number. Okay, so there are 4 quantum numbers. One of them is n. N is we call the principal quantum number: 1, 2, 3, 4, 5, 6, etc. Okay, so this is the principal quantum number. So only those orbits are possible for which the angular momentum is n times h over 2 pi. This is your second postulate. And those orbits, if you want to know the radius of the orbit is Rn. This is the radius of the orbit. N is 1, 2, 3, 4, 5 like this. This is equal to 0.53 times 10 to the power, I think it is negative 10 meter times n square. So if you have to calculate the radius of the orbit, circular orbit, the radius Rn is equal to 0.53 times 10 to the power negative 10 times meter times n square. So what is n? N is 1, 2, 3, 4, 5, 6, 7, 8 like this. So if you want to figure out like a R1, the first orbit, okay, you have to write down like this: 0.53 times 10 to the power negative 10 meter times 1 square. So this is how you figure out the radius of the circular orbit, any circular orbit. Okay, so any means those orbits that satisfy this condition. Angular momentum is integral multiple of h over 2 pi. So you can make this is the second postulate. Okay, so I told you that when electrons are moving in a stationary orbit or circular orbits, okay, it does not radiate energy. If the electron is moving in a circular path, it doesn't radiate energy. But if the electrons are jumping from one energy level to another energy level, we say when the electron make a transition between two energy level, you can write down like this is energy level n equal to 1. Here you have energy level n equal to 2. Here you can write down energy level n equal to 3, and you have energy level n equal to 4, and you have energy level n equal to 5, something like this. Okay, you can draw the energy level of the electrons. So if the electrons is simply moving in a circular path, it does not radiate energy. It does not radiate energy. And here look, there are different, we call energy level. Okay, they are the energy level, and if you want to calculate the energy of every state here, n equal to 1, n equal to 2, n equal to 3, for hydrogen atom, for hydrogen, the energy level En equal to negative 13.6 divided by n squared electron volt. This is the energy of each level. So for example, if you want to calculate n equal to 1, the energy level of this state, you have to write down E1 equal to negative 13.6 divided by 1 square electron volt. So see, this is simply negative 13.6 electron volt. So this state has an energy negative 13.6 electron volt. Now if you want to calculate this state, plug n equal to 2 here. Plug n equal to 2 here. Then if you want to calculate this state, plug n equal to 3 here. You can get the energy of the different state. And this is for the hydrogen atom. Hydrogen atom is kind of important, okay? And if you want to calculate for other atom, you have to multiply this by atomic number G square. So forget about this right now, okay? So just hydrogen atom is good enough. So I said when the electron is, if the electron is moving in a circular path, it does not radiate energy. It doesn't release any energy. There is no energy if the electron is moving in a circular path. But if the electron make a transition from one energy level to another energy level, so electron is here, this electron jump from second energy level to the first energy level. In this case, energy release. If the electron jump from higher energy level to the lower energy level, in that case the energy release. And the energy release here E, the energy release E, this is equal to energy of the higher level minus energy of the lower level. If the electron jump from higher energy level to lower energy level, then in that case the energy release. And the released energy is energy of the higher level, this energy, let me call this is E2, this is E1, okay? E1 is negative 13.6, I don't know, E2 you can plug n equal to 2 here, so it is 4, so it is E2 is 3 point something electron volt, okay, 3 point something electron volt. So if the electron jump from second energy level to the first energy level, in that case the energy release E equal to E2 minus E1 then. So you don't have to do all mathematics here, that is not necessary for you, but what you need to know is if the electron jump from higher energy level to the lower energy level, in that case energy released, and the released energy is this is the released energy E, this is equal to energy of the higher level minus energy of the lower level. That's it. So this is another postulate of the Bohr's model. This is I think third postulate. Okay, so please know this. And the Bohr's model simply, we can calculate the energy of the hydrogen atom. This energy, this is the formula to calculate the energy of the different state of hydrogen atom. If you plug n equal to 1, you get negative 13.6 electron volt. This is called as the ground state of the hydrogen atom. Okay, so this is about the Bohr's model. And then we have to talk about the the de Broglie hypothesis. De Broglie hypothesis. The electron behaves like electron is a particle. Like the mass of the electron me, this is 9.11 times 10 to the power negative 31 kg. But according to de Broglie hypothesis, the light is photon, and the light, it is a wave. But the photon, it behaves like a particle also. We learn photoelectric effect, we know also the Compton effect. So light behaves like a particle, light behaves like a wave. So light has a dual property, wave light properties and the particle light properties, duality, photon. So if the photon has a dual property, wave nature and particle nature, de Broglie, he claimed that every object, including proton, electron, or whatever object, even like our car, if the car is moving, it behaves like a wave. Car, of course, it is a particle, it is an object, particle nature. But if the object is moving, it has a wave nature also. So if the electron is moving, it has a wave nature and it has a particle nature both. So if the object behaves like a wave nature, that material, that object must have a wavelength, then we call that material wave. So the material wavelength lambda, this is equal to h divided by p. De Broglie hypothesis, the lambda, material wavelength, lambda equal to h over p. What is lambda matter wavelength. Okay, this is matter, or simply you can say matter wavelength. What is P? P is, you know that P is a linear momentum, mass times mv. Okay, mass, m is the mass, v is the velocity. So if it is an electron, then you have to use this mass, 9.11 times 10 to the power negative 31 kg. So momentum is m times v. And what is h? I told you many times. H is a Planck's constant. It is 6.626 times 10 to the power negative 34 joule sec. So this is the the wavelength momentum. If you have to calculate the momentum, then P equal to h over lambda then. And here, if you plug this m, 9.11 times 10 to the power negative 31 kg, we simply use a non-relativistic mass. Non-relativistic mass. You know, there is a relativistic mass is like m relativistic. This is equal to m0 divided by gamma. We learned this already in a special theory of relativity. This is a relativistic mass. Similarly, you have a relativistic momentum. But here, I simply use the non-relativistic momentum. So, de Broglie hypothesis, you can use the wavelength, material wavelength, lambda equal to h over p. So, please recall this. You don't need more than this, just this formula, keep in mind. Okay. So, this is one thing I want to remind you, and there is another principle, we call that is Heisenberg uncertainty principle. Heisenberg uncertainty principle. The Heisenberg uncertainty principle is simply related to the position and momentum, one pair, energy and time, like this. So according to this principle, if you measure the position of any particles precisely, you cannot measure the momentum precisely. If you measure the position of any particle precisely, you cannot measure the momentum precisely. You will get some uncertainty in momentum. Or the other way, if you measure the momentum precisely, then you will get some uncertainty in the position measurement. So, if delta x is the uncertainty in position, delta x, this is uncertainty in position, and delta p, this is uncertainty in momentum, then this product is greater than or equal to h over 2 pi. This is Heisenberg uncertainty principle. So Heisenberg uncertainty principle, if you want to write down the statement, you can say something like this. It is impossible to measure the position and the momentum of the particle at the same time precisely. It is impossible to measure the position and the momentum of the particles at the same time precisely. If you measure the momentum precisely, you will get certain uncertainty in the position and vice versa. Okay, so the product of uncertainty in position and the uncertainty in momentum, which is greater than or equal to h over 2 pi. This is the Heisenberg uncertainty principle. Similarly, if you measure the energy precisely, you cannot measure the time precisely. So simply the product uncertainty in energy, uncertainty in time is also greater than or equal to 2 pi. This is your uncertainty principle again. But here this is energy and time pairs, and this is position and momentum pairs. Okay, so better to know this, just the statement only. Then I don't have a time today to talk about the special theory of relativity. I just posted the the video, so please watch that. Okay, you have time dilation formula, delta t equal to delta t0 square divided by 1 minus v square divided by c square, and you have to take a square root. This is the time dilation formula. This is the proper time, and this is the time observed by the observer on the surface of the earth. So these two times, they are two different frame of reference, measured from the two different frame of reference. So please watch that, and I strongly recommend you to read the textbook also. Okay, my video is not enough. I briefly talk about the relativity only, briefly. So I strongly recommend you to read the textbook. So you need this formula, and there is another formula. This is a time dilation formula, and there is another one, L equal to L0 times square root 1 minus V square divided by C square. This is a length contraction formula. Okay, but you also have to learn the postulates of the special theory of relativity. What are the postulates? The laws of physics are same in all inertial frame of reference. Inertial frame of reference, non-accelerating frame of reference, where you can apply the Newton's first law. That is the inertial frame of reference. Laws of physics are same for in all inertial frame of reference, number one. And number two is the speed of light is constant in a vacuum. In a vacuum, the speed of light is constant irrespective of the motion of the source of light or motion of the observer. For example, let us suppose you are in the space. You are inside the rocket. You are moving in the space and you are measuring the velocity of light. So what is the velocity of light? What is your velocity of light? 1c, 0.5c, 0.8c. So what is the velocity of light? You are measuring. You are in the space, not on the surface of the earth. You are in the space, in the vacuum, in the rocket. And you measure the speed of light. What is the speed of light then? Your rocket is moving with high speed. Your rocket is moving with high speed. So what is the speed of the speed of the light then? What do you think? Which one is correct? Keep in mind, the speed of light is constant in the vacuum, irrespective of the motion of the observer or motion of the source of light. So answer is always 1c. 1c or simply c, because c is 3 times 10 to the power 8 meter per second. This is constant. This is the postulates of the special theory of relativity. So even though your rocket is moving with high speed, but still the speed of light is constant, because that is the postulate. The speed of light in the vacuum is constant irrespective of motion of the observer or motion of the source of light. So please recall that. That is from the special theory of relativity. Then the rest is nucleus. Okay, the nucleus. You know, you have to start from here. The nucleus is simply represented by this. This is the chemical symbol. Here you have a Z and here you have a A. G. This is the atomic number. I think if you watch the video chapter 33-34, I think that video is good enough to prepare for the quiz. So I think I explained the things clearly there. So G atomic number. What is atomic number? Atomic number is number of protons. Number of protons. This is atomic numbers. Okay. What is A then? This is atomic mass number, or simply you can call mass number also. So this is G plus N. G is the atomic number, N is the number of neutrons. This is number of neutrons. Okay. So if you want to calculate, this is A. Okay. So if you want to calculate the number of neutrons, this is A minus G then. So to calculate the number of neutrons. Okay. So you know, in an atom you have a proton, neutron and electron. In the nucleus you have only the proton and the neutron. And the proton and neutrons, they are sitting together in the very small region. Neutron has a no charge, neutral, but you know that the proton has a positively charged, but still they are sitting together. But as we know that like charge, proton and proton, they repel. There is a repulsive force. We learn that in electrostatics. But how come the protons, they are sitting together? That means there must be another force. So that force bring the protons together, keep the protons together inside the nucleus. We call that strong nuclear force. So the strong nuclear force bring the proton and the neutron together. They are sitting together. But the strong nuclear force, it is short range force. Strong nuclear force, strong nuclear force, this is short range force. This force exists only if the distance between the proton is only like 10 to the power negative 15 meters. If the distance between two proton is only within this range, 10 to the power negative 15 meters, short range, okay, then you can see the strong nuclear force. Okay, so the strong nuclear force is responsible to bring the protons together, or simply you can say that keep the proton neutrons together inside the nucleus. So keep this here, and like the element nucleus, you have a hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium. You go higher and higher and higher, like starting from hydrogen you go up to uranium. Hydrogen has like one proton, one electron. There is no neutron. Simple hydrogen, it is one electron, one proton, one electron. But you can see the isotopes of hydrogen atom also. Hydrogen has 3 isotopes. What is isotopes? What is isotopes? Same atomic number, but different atomic mass number. So this is called as the isotopes. For example, you can write down 1H1. This is hydrogen. You can write down 1H2. This is also hydrogen. You can write down 1H3. All three, they are hydrogen. 1H1, atomic number is 1, atomic mass number is 1. Here atomic number is 1, atomic mass number is 2 here. Different. Atomic number is 1, atomic mass number is 3. So different atomic mass number. This different, but same atomic number. This same number of proton, but different number of neutrons. That is called as the isotope. So isotope, they are the same element, only the atomic mass number is different. Okay. So here I have a hydrogen, and let's say the uranium is 92. You can write down 236. One isotopes of the uranium nucleus. There are uranium also has a isotopes. Okay, so they are hydrogen to uranium. Hydrogen is the first element, uranium is the 92th, and they are hydrogen to uranium. They are naturally available in the environment, but nowadays we have more than 92 elements. Scientists, they discovered the element in the lab artificially. They make a nucleus that is artificial. I am talking about only the naturally available. Naturally we have only 92. So the size of the nucleus is increasing. If you go higher and higher, hydrogen has the smallest one. After that, after hydrogen, you have a helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon. They are in order, go higher and higher. And the size of the nucleus also increase. So if you take the bigger one, the B one, this is the uranium is the biggest one naturally available. The uranium nucleus is unstable. There are more proton, 92 proton here, they are unstable. So the unstable nucleus decay, split into the a new nucleus. For example, if you keep the if you have some, let's say here you have some radioactive element right there. If you have some radioactive element right there, then the radioactive element disintegrates, decay itself. Okay, and in that process it emits the 3 different types of ray. One is it goes like this. We call this is gamma ray. Gamma ray is simply, it has no charge. It is not related to the charge. That is why if you keep the a magnet here, this is a magnet to create the magnetic field. Even though the gamma ray it does not deflect, it goes straight. That is a gamma ray. Okay, gamma ray. So in disintegration, decaying process, this is, you can say, gamma decay also. And another one is like alpha particles. Alpha particles. This is alpha particles. Alpha particle. Alpha particle is helium nucleus, positively charged, deflect by the magnetic field. And another one is gamma particles. Gamma particles. Gamma rays, no charge, no deflection. Gamma rays, no deflection. Another one is alpha particles. Alpha particles. And the other one is beta particles. Beta particles. Alpha particles and beta particles, they are deflected by the magnetic field, because beta particle is electron, negatively charged. Beta particles, this is electron. Beta particle is electron, negatively charged. Negatively charged. Negatively charged. Alpha particles, it is helium nucleus, 2He4, helium nucleus, positively charged. Positively charged. Okay, so you have a 3 decay: gamma decay, beta decay, and alpha decay. So don't forget, gamma, it is a neutron. Okay, no charge. Alpha particle positively charged, beta particles negatively charged. Beta particle is electron. Okay, so let me talk about the alpha particles, which is helpful for the exam also. In alpha decay, if a nucleus goes alpha decay, let us suppose this is your nucleus, any nucleus. It has an atomic number G and atomic mass number A. If it goes alpha decay, what happens? What is your new nucleus then? The new nucleus has atomic number G minus 2 and atomic mass number is A minus 4, plus here you have, it is alpha decay, so the alpha particle is there. So if the nucleus go alpha decay, we call this nucleus, we call parent nucleus. Parent nucleus, and this is called as the daughter nucleus. Daughter nucleus. Okay, so the parent nucleus and daughter alpha particle is there. This is also you can call daughter nucleus, but simply we call alpha particles. So the daughter nucleus has atomic number 2 less than the parent nucleus. You need this G minus 2 number, 2 decrease, 2 less than this G. Atomic mass number 4 less than this A. This is your alpha decay. Similarly, you have to learn beta decay, beta decay. Beta decay, the electrons released there. In that case, the beta decay is completely different. In beta decay, the parent's nucleus has the proton number increase, and gamma, nothing changed, because gamma is a neutron. So please look at my video today. I don't have a time. Okay. And talk about the gamma, beta, and please read the gamma, beta, and alpha decay, and you also learn about the half-life. Okay, time taken to decay half of the original atom. If you have a 1 kg uranium today, okay, how long it takes to become half kg? That time is called as the half-life. That took a long time. Even if you have like 1 gram today, and to become half gram, how long that takes? That is a half-life. Time taken to become half. That is half-life. And there are 2 formulas. One is n equal to n0 e to the power lambda t. This is called as the radioactive decay law. Radioactive decay law. You need this. Okay. And another one is the half-life. T half, this is equal to 0.693 divided by lambda. This is a half-life. Don't confuse this lambda. This is not wavelength. We call decay constant. Lambda, this is your decay constant. Lambda is the decay constant. Okay. What is T half? T half, this is the half-life. Half-life. What is N0? N0 is number of atom or particles, whatever, number of particle at t equal to 0, original atoms, original number of particles. Here, this n0. And what is n? N, this is also number of particle at any time t. So time t equal to 0. If you start to measure the time right now, t equal to 0, after 5 seconds, 10 seconds, that is t. Okay, so t0, t equal to 0, you can simply call that is the beginning, initial. Okay, so this, you need this. So if you want to let us suppose right now there are 100 particles. Right now there are 100 particles. How many particles will remain after 20 seconds if the half-life is given, if the decay constant is given? Right now, let us suppose there are 100 particles. So n0 is 100. How many particles remain after 1 day? So that means what is n after 1 day? Your time is 1 day. Decay constant is given. It is a constant. It is given. Okay. So please look at this formula also. Okay. So the video is already long. So please watch the video chapter 33, 34. Watch the video, special theory of relativity, and of course this video also help you. And again in the video, the chapter 33, 34 video, I said that you have a third exam and you have a final is optional. I said something like that, but that video is from my last year's class. So your final is not optional, everyone. You have to take the final exam, everybody. Final exam is mandatory, because this semester I plan to give you only 3 exams. I already gave you the first exam, second exam. Now you have a final exam. Everybody, you have to take the final exam. Otherwise, you fail the class. No matter what grade you have right now, but if you miss the final exam, you fail the class. It is important, okay? Thank you.